Hi everyone. Today we're going to explore the nature of light and its importance for life. We'll discuss the units of light, such as wavelength, frequency, and energy. We'll examine the dual nature of light as both a wave and a particle, and we'll see how understanding the electromagnetic spectrum helps us comprehend how plants capture light energy for photosynthesis. Let's start with a question that puzzled scientists for centuries: is light a wave or a particle? To understand this, let's first define what we mean by wave. A wave is a disturbance that transfers energy from one place to another without moving matter over long distances. For example, consider the ripples on a pond. When a stone is dropped into a body of water, it creates a series of circular ripples that spread out across the surface. These ripples carry energy away from the point where the stone was dropped, but the water particles themselves do not travel far. They simply move up and down. So, how does light work? Well, as we know, light travels in waves, but what exactly does that mean? To answer that question, let's look at some characteristics of waves. Waves are typically described by three main properties. First, there's wavelength, which is the distance between two successive crests or troughs of a wave. Second, there's frequency, which is the number of waves that pass a particular point in 1 second. And third, there's speed, which is how fast the wave travels. For light waves, these properties are related by the following equation: c equals lambda v, where c represents the speed of light, lambda represents the wavelength, and v represents the frequency. Since light travels at a constant speed of approximately 3.0 times 10 to the 8 meters per second, the wavelength and frequency are inversely related. Now let's consider what happens when light waves interact with matter. In some cases, light waves can be reflected, meaning they bounce off a surface. In other cases, they can be refracted, meaning they bend as they pass from one medium to another, such as from air to water. These phenomena can be explained by considering how the electric and magnetic fields of the light wave interact with the atoms and molecules of the medium they are traveling through. In the next section, we'll delve into the concept of light as a particle. Before that, let's solidify our understanding of light as a wave. So far, we have learned that light travels in waves, and we have seen some of the characteristics of these waves. Let's now explore the nature of light as a particle. We know that light can exhibit properties of waves, such as reflection and refraction. However, it can also behave like a stream of tiny packets of energy called photons. According to quantum mechanics, every photon carries a specific amount of energy that is proportional to its frequency. This relationship is described by the following equation: E equals hv, where E represents energy, h represents Planck's constant, and v represents frequency. This equation tells us that the energy of a photon is directly proportional to its frequency. This means that higher frequency light, such as blue light, has more energy than lower frequency light, such as red light. These concepts may seem counterintuitive because we are used to thinking of energy as something that can take on any value. However, in the quantum world, energy is quantized, meaning it comes in discrete packets. This is a fundamental concept in understanding the behavior of light and other forms of electromagnetic radiation. Now that we've covered the basics of light as both a wave and a particle, let's move on to the electromagnetic spectrum. The electromagnetic spectrum is the range of all possible frequencies of electromagnetic radiation. While we can only see a small portion of this spectrum, known as visible light, electromagnetic radiation encompasses a much wider range of frequencies, including radio waves, microwaves, infrared radiation, ultraviolet radiation, X rays, and gamma rays. The electromagnetic spectrum is continuous, meaning that there are an infinite number of frequencies present. Different frequencies of light interact with matter in different ways. For example, radio waves are used in communication systems because they can be easily transmitted and received over long distances. Infrared radiation is used in night vision goggles because it can penetrate darkness. Visible light is the only portion of the electromagnetic spectrum that is detectable by the human eye. This range of frequencies that we can see is relatively small compared to the entire electromagnetic spectrum. Finally, let's explore how the absorption spectrum of chlorophyll helps us understand how plants capture light energy for photosynthesis. As we mentioned earlier, plants absorb light primarily in the blue and red portions of the visible spectrum, reflecting green light, which is why most leaves appear green. This selective absorption is due to the chemical structure of the pigment chlorophylla. When light hits a leaf, some of it is absorbed by the chlorophyll molecules. If the energy of the photon matches the energy difference between the ground state and an excited state of the chlorophyll molecule, then the photon is absorbed and the chlorophyll molecule becomes excited. The excited state is unstable, however, and the chlorophyll molecule quickly returns to the ground state, releasing the excess energy as heat or light. By analyzing the spectrum of light that is absorbed or reflected by a leaf, we can gain insights into the types of light that plants use for photosynthesis and the efficiency of different pigments in capturing light energy. And that's a wrap. I hope you enjoyed this journey through the nature of light. Thank you for watching. Until next time.